Hello everyone, welcome to my channel. This is an educational channel focused on bringing to light unknown or mostly unknown um, theories of everything, all-encompassing theories, uh, work of heroes of mine who've spent their whole life working on something, never really got rewarded or got their theories out there too far, um, but they're valuable, or at least I think they are. Today is number 181, video number 181 on the reciprocal system of theory. And this is a system of theory that was first derived by Dewey B. Larson back in the 20th century, starting way back in about 1930, all the way up until his death in 1990. The reciprocal system of theory basically posits that we live in a universe of motion. The universe is not made out of matter, it is not made out of energy, but it is made out of motion. And motion is the relationship between space and time. Space and time are therefore not the container of the universe, but they are the contents of the universe. And space and time have a generalized reciprocal relationship. I mentioned this yesterday. I didn't really follow through on the whole analogy. Now, the most basic idea of motion that we know, speed. The car is moving 20 miles per hour. That is 20 miles of space in 1 hour of time. Space over time equals speed. And we can see the reciprocal relationship if we decide to double the speed. So we say the car is moving 20 miles an hour. Well, you could say instead that if you double the speed, you could say the car is now moving 40 miles per hour. But showing the reciprocal relationship between space and time, you can also say that the car is moving 20 miles per half hour. Both of them are the same. You can either multiply the first or you can divide the second. There's a reciprocal relationship there. But not only that, all scientific quantities are relationships between space and time. That's because space and time are multidimensional. They both have what Larson calls their coordinate aspects. Now, we recognize that time generally has XYZ coordinate, or space generally has XYZ coordinates, or in some cases even more than 3 dimensions. But time also has multi-dimensions. So when you express motion, you can use multiple dimensions for either the numerator or the denominator. So speed is a very simple kind of motion, space over time. But you can get more complicated. Say if you wanted to say acceleration, acceleration is space over time to the second power. Capacitance is space to the third power over time. And magnetic flux, you can reverse the two, and magnetic flux is time to the second power over space to the second power. Matter is time to the third power over space to the third power. Energy is simply time over space. And so on and so forth. And so space and time both have their coordinate aspects. They also have their clock aspects, which is a scalar motion. Scalar motion is a motion that has a magnitude but has no direction, or no particular direction. It really only has in or out. And you would imagine this by imagining a balloon, putting a bunch of dots on the balloon with a magic marker, and you blew up the balloon. All of the dots are moving away from each other. That is an outward scalar motion. You suck in the balloon, and all the dots are moving toward each other. That's an inward scalar motion. And that is what Larson calls clock time and clock space. The clock of time, the clock is always getting later and later and later. And with the clock of space, the clock is always getting farther and farther and farther apart, just like a, an expanding balloon, the points on the surface of an expanding balloon. Now, space-time also have their discrete units. There is a minimum unit of space and time. There is no continuity. They come really only in chunks. So there's a minimum unit of space and a minimum unit of time. And if you have just one unit of space in one unit of time, you have the speed of light. So really the speed of light is one. You can think of this as really the midpoint of the universe, the neutral point, or the origin of the universe, or even the ether of the universe is the speed of light. And then that means that half the universe is moving slower than the speed of light. This is the half that the scientists are aware of, and that's why that's why Einstein said that the speed of light is the maximum speed of the universe, because he didn't know about the other half of the universe, which Larson calls the cosmic sector, where the speed of light is the minimum speed of the universe. Everything in that universe is moving faster than the speed of light. So you have the material sector and the cosmic sector. We know all about the material sector from legacy science. We know nothing about the cosmic sector. But because of the reciprocal relationship between space and time, we recognize that what's going on in the cosmic sector is exactly the same as what's going on in the material sector, except you have to invert the roles of space and time. And so we can extrapolate to understand everything about this cosmic universe, or half of the universe. Okay, now we are looking at Larson's book called Nothing But Motion. And this book came out in 1979. It's the first of 3 volumes of what he calls the structure of the physical universe. This book is primarily on physics, with a little bit on organic chemistry at the end. And we are in chapter 11 of this book. This chapter is called Subatomic Particles. And we just went through his identification of the positron and the electron with his notation. Remember, he's got his ABC notation. A is now the atoms and subatoms are made up of combinations of motions. You first start, you have 4 different kinds of motion. You have a translational motion, you have a vibrational motion, you have a rotational motion, and you have a rotational vibration. And these can come in multi-dimensions as well. And the atom is basically a combination of 2 primary two-dimensional rotations, which Larson calls magnetic, and a secondary two-dimensional rotation, and then an optional electric rotation, which is a one-dimensional rotation. So those are the 3 numbers, A, B, and C. That is primary magnetic, secondary magnetic, and electric. The electric is optional. It's only for the atoms that are not noble gases, that are not inert. So it means the vast majority of them, but it's not necessary. If that number is 0, then you're looking at a noble gas. Okay, we will start right here and pick up Larson's discussion on the electron. As brought out earlier, adding motion with negative displacement has the effect of adding more space to the existing physical situation, whatever it may be. And the electron is therefore, in effect, a rotating unit of space. Now that's a difficult concept to probably grasp, but that is really what the definition of the electron is that he uses. The electron is a rotating unit of space. This is really the inverse of a motion, a motion that is moving through space, something moving through space. This is a unit of space moving through time. The relationship between space and time is motion. So if you have a rotating unit of space, that unit of space has to be moving through time. So the electron is a rotating unit of space, and it only can move through time. We will see later that this fact plays an important part in many physical phenomena. One immediate and very noticeable result is that electrons are plentiful in the material environment, meaning in the low-speed environment, whereas positrons are extremely rare. On this basis of the same considerations that apply to the electron, we can regard the positron as essentially a rotating unit of time. And so therefore the positron is only going to be moving through space. And as a result, is not going to be within an atom, which is made out of time. So the positron is very rare in the material environment, but in the cosmic environment is plentiful. As such, it is readily absorbed into the material system of combinations, the constituents of which are predominantly time structures. That is, rotational motions with net positive displacement. The opportunities for utilizing the negative displacement of the electrons in these structures, on the contrary, are very limited. If the addition to the rotational base is a magnetic unit rather than an electric unit, the result could be expressed as M material 1-0-0. It now appears, however, that the notation M 1/2-1/2-0 is preferable. Of course, half units do not exist, but a unit of two-dimensional rotation obviously occupies both dimensions. To recognize this fact, we will have to credit 1/2 to each. The 1/2-1/2 notation also ties in better with the way in which this system of motions enters into further combinations. We will call this M 1/2-1/2-0 particle the massless neutron for reasons which will appear shortly. Now, this again is a difficult notational issue, because Larson is emphatic that saying with his discrete unit postulate, saying that there is no such thing as less than one unit. But here he comes with the notation 1/2-1/2-0. And he explains, of course, half units do not exist, but the unit of two-dimensional rotation obviously occupies both dimensions. So we're going to use this notation 1/2-1/2-0 for what he calls the massless neutron. Now, Bruce Perret, among others, insisted that this 1/2-1/2-0 particle was actually the muon neutrino. But so we will eventually cover Bruce Perret's material, but right now we're looking at Larson, so we will go with his concept of the massless neutron. At the unit level, in a single rotating system, the magnetic and electric units are numerically equal. That is, 1 squared equals 1. Addition of a unit of negative electric displacement to the m 1/2-1/2-0 combination of motions, the massless neutron, therefore produces a combination with a net total displacement of 0. This combination, m 1/2-1/2 1/2-1/2-1, can be identified as the neutrino. And I think Perret would just call this the electron neutrino. In the preceding chapter, the property of the atoms of matter known as atomic weight or mass was identified with the net positive three-dimensional rotational displacement of the atoms. This property will be discussed in more detail in the next chapter, but at this time we will note that the same relationship also applies to the subatomic particles. That is, these particles have mass to the extent that they have net positive rotational displacement in 3 dimensions. None of the particles thus far considered meets this requirement. The electron and the positron have effective rotation in 1 dimension, the massless neutron in 2. The neutrino has no net displacement at all. The subatomic rotational combinations thus far identified are therefore massless particles. So in order to have mass, you have to have displacement in all 3. You have, what does he say? Net positive 3-dimensional rotational displacement. They have mass to the extent that they have net positive rotational displacement in 3 dimensions. Okay. By combination with other motions, however, the displacement in 1 or 2 dimensions can attain the status of a component of a 3-dimensional displacement. For instance, a particle may acquire a charge, which is a motion of a kind that will be examined later in the development. And when this happens, the entire displacement, both of the charge and of the original particle, will then manifest itself as mass. Or a particle may combine with other motions in such a way that the displacement of the massless particle becomes a component of the 3-dimensional displacement of the combination structure. Addition of a unit of positive instead of negative electric displacement to the massless neutron would produce m 1/2-1/2-1. But the net total displacement of this combination is 2, which is sufficient to form a double rotating system, an atom. And the greater probability of the double structure precludes the existence of the m 1/2-1/2-1 combination other than momentarily. Meaning it can form, but it immediately decays. It's immediately radioactive and turns into photons. The same probability considerations likewise exclude the 2-unit magnetic structure of m1-1-0 and its positive derivative m1-1-1, which have net displacements of 2 and 3 respectively. However, the negative derivative m1-1-1 formed in practice by the addition of a neutrino, which is m1/2-1/2-1, to a massless neutron, m1/2-1/2-0, can exist as a particle as its net total displacement is only 1 unit, not enough to make the double structure mandatory. This particle can be identified as the proton. So the proton is 1, 1, -1 in Larson's system. Here we have an illustration of the way in which particles that are individually massless, because they have no three-dimensional rotational, combine to produce a particle with an effective mass. But the massless neutron rotates only two-dimensionally, while the neutrino has no net rotation. But by adding the two, a combination with effective rotation in all three dimensions is produced. The resulting particle, the proton, m1-1-1, has 1 unit of mass. At the present rather early stage of the theoretical development, it is not possible to make a precise evaluation of the probability factors and other influences that determine whether or not a theoretically feasible rotational combination will actually be able to exist under a given set of circumstances. The information now available indicates, however, that any material type combination with a net displacement of less than 2 should be capable of existing as a particle in the local environment. In actual practice, none of the single system combinations identified in the preceding paragraphs has been observed, and there is considerable doubt as to whether there is any way whereby they can be observed other than through indirect processes which enable us to infer their existence. The neutrino, for example, is observed only by means of the products of certain events in which this particle is presumed to participate. The electron, the positron, and the proton have been observed only in the charged state, not in the uncharged condition, which constitutes the basic state of all the rotational combinations thus far discussed. Nevertheless, there is sufficient evidence to indicate that all these uncharged structures do, in fact, exist and play significant roles in physical processes. This evidence will be forthcoming as we continue the theoretical development. Okay, that is it for today, and thanks for tuning in. We will take over again tomorrow when we start up and go further through this chapter on subatomic particles. Thanks for tuning in. Have a great day.